Great, thanks a lot. Thanks a lot, Ananda, and for the introduction, and also the organizers for this nice timely meeting. I'm going to change the gear a little bit now, and we have heard excellent talks this morning on several electromagnetic proofs to the universe, and which has helped us in building the standard model of cosmology. And as my title says, I'm going to tell you how gravitational wave observations are going to be particularly useful in this decades-long endeavor of getting our cosmology right. Okay, so long story short will be that this is the history of the universe that we have learned so far in using several electromagnetic observations, primarily driven by cosmic microwave background from high redshift, you heard this morning, and also from the low redshift universe using several galaxy surveys, supernova observations. Some of those will be told to you in the coming days. What's interesting is that this particular mapping, which has been done from several electromagnetic observational probes from gamma rays to radio, connecting multi-billion observational data to get to the lambda cold dark matter universe, there is a growing tension of several problems. What you have seen is challenges or tensions are not just unknown, but it's just going to be there, whether you're talking about Hubble constant tension or sigma E tension, but forget about those. There are some tensions which are even much longer, which can be connected to how black holes are formed in the universe, how have black holes grown in the universe, how the universe was back at the high redshift, as you have already started hearing, that there are many more surprises which JWST observations is bringing to us. So this mapping is definitely a question now, where possibly at some places gravitational waves can make it as very simple, nice probe which is a better and deeper in some aspects than the other. So just to understand how gravitational waves actually is a better and a deeper probe to the universe to understand the lambda cold dark matter. So the good part is that we don't understand our standard model. So it's not yet on the book for us to say that we have understood everything. We have a more long list of things we have never understood. So a lot of work to be done. So that's the message for the students and postdocs. There are a lot of things to do to really make a standard model of cosmology stands in the fit of data. And what really gravitational helps in bringing is that it's a probe which can go very deep. It can see the universe up to high redshift, thanks for its very weakly interacting property with foreground, so-called dust contaminations are not there. Several advantages by which we can actually go to very high redshift. To be just, I will not talk about this much, but I'm presuming there will be some talks at the end of the, in some part of this meeting, telling you about that we can actually go to the very early universe much deeper than what you can go to CMB, because there is no such thing as optical depth. I can really use stochastic gravitational background to go very deep in the universe. And thanks to a lot of engineering frontiers which has really helped us in getting to this particular scenario now, where you are able to measure gravitational wave in multiple bands. As like electromagnetic signal, gravitational wave comes in multiple spectrum from very low frequency, which you can see from cosmic microwave background. Today morning, Rishi and Tuhin talked about it, to the extent of a very high wavelength frequency, high frequency signal, which is seen from LIGO Virgo Kavra and in near future from LIGO India, which are particularly coming from stellar origin binary black holes. And in between I have two more windows which are funded and operational. One is the nanohertz gravitational waves, good in seeing the supermassive binary black holes in the universe, and the millihertz gravitational waves, which are particularly excellent probe to see the millions to thousands of solar mass black holes. So what I plan today, that I definitely cannot cover a lot of aspects which we work on. I'm going to give you an overview on some of the interesting things. You already heard Harsh on nine gravitational aspects this morning. I'm going to particularly focus on the gravitational wave part, and I will tell you how the gravitational wave observations is something which is extremely fascinating, in my opinion, in these four regimes: length, redshift, source, time scale. You can see a source up to very high redshift, as I just now argued, with the help of ongoing and upcoming detectors, way up to a shift of few tens to close to 100. I can see a single source which can be written in terms of first principle emission mechanism using general theory of relativity from a few seconds or milliseconds to time scale of a years. I can see a source in Lisa for years instead of which I see in LIGO for a few hundreds of milliseconds to a few seconds. These sources are of all different kinds, from binary neutron star to supermassive binary black holes. So you can possibly understand I can measure a signal in phase up to very high redshift whose amplitude can be given from the first principle. And very interestingly, these for all aspects I can explore physics from scales of a few kilometers when the black holes are very nearby, the scales of cosmological scales, because cosmic expansion history of the universe gets imprinted on the gravitational wave signal. And this really, what it brings to us is the way to map the entire expansion history of the universe in terms of very different kinds of sources. Instead of talking about cosmic microwave background like photons, or instead of talking about galaxy surveys, quasars, now we have a different tracer of the universe. It's a tracer, it's a binary black hole of all different masses. Binary neutron star and neutron star black hole systems, using which will go up to very high redshift universe, and as a result, it naturally becomes a probe to cosmology, and can possibly answer several of your questions, and depending upon what is your interest, you can find your favorites. I'm going to cover a little bit today on some of the parts which has been seen from the data as so far using LIGO camera, and some aspects which will be opening up using nanohertz, using SK observations. So at first I'll talk about gravitational emissions from sources with EM counterpart and without EM counterpart. The one which is marked in circle is the most promising one, most precise, but fewer in number. And the other one is more in number, but each of them are not very precise. And we have seen about one of these and about hundreds of them. So these are the binary black holes. Why is it becoming an extremely important aspect to measure the expansion history of the universe, whether it's physics or systematics? So the way I put it, there is an ignorance of ours in either modeling cosmology or modeling astrophysics. There's a problem somewhere. And the long story short is that there are two inferences of Hubble constant from low redshift and high redshift probe. They don't agree with each other. I'm pretty sure this community don't need an introduction to this particular topic, but we can talk about this later during coffee in case you need some more clarification. But I'm going to talk about this about results on gravitational waves, which has provided weak but first measurements using multi-messenger signal using gravitational waves. So there exist two ways to measure it. If I can see the electromagnetic counterpart to the gravitational wave source, like source having a neutron star or neutron star black hole, or a source without a black hole. And the way the technique works is that if I give you this bunch of stars, if I tell them like a gravitational wave source, they're not going to follow the underlying distribution randomly, but they're going to follow the distribution of the background structures. So these are the places where structures form, high density regions where I can expect to see galaxies and black holes, and as a result, I can possibly explore something called as clustering between gravitational wave sources and galaxies for those sources which has better style localization error. So how this works? So I have to combine two different probes. I have to combine two different probes. In one side, I have a good distance tracer, which are the gravitational wave sources. On the other side, I have a good redshift tracer, which are like spectroscopic galaxies, such as DAISY, and in very near future data will be available from SphereX and Euclid. As a result, one can do spatial clustering measurement of gravitational wave sources and galaxies to infer their clustering redshift. A very promising window, and its first application is done on GWTC3 for the very well localized gravitational wave sources. Sources for which we have sky localization error less than 30 square degrees. Only 8 in number out of 90 of them, about 94 of them, so about 10%. This 10% will grow with LVK and with LIGO India. But right now, this is a measurement we have. It tells us that the weak but first measurement using gravitational wave sources by both GW17 which is a bright siren, along with the cross correlation technique shown by both of them together in black. And these two are the measurements by Planck and Schulz which disagree. The idea is in little long run, I will not have time to talk about this, but we have shown that using this particular technique, we will be able to reach about the 2% measurement with about 300-ish gravitational wave sources in the era of LVK, and with LIGO India it will be even more powerful. What do we need? We need a good sky coverage survey in spectroscopically, and that is possible from DESI, Euclid, and partly from SphereX. Moving on, a very interesting aspect which is now coming up is measurement of dark energy equation of state, and rather we have started seeing possible deviations from lambda in this particular sector thanks to observations from DESI. But how accurate and how reliable are these measurements? One of the particular thing to understand is that when you start to infer distance from an astrophysical source such as supernova, there is no standard model of astrophysics I can use to get the luminosity correctly. As a result, distance is a very difficult thing to measure. Instead of redshift, where I can use the spectrum and measure the redshifts. Gravitation brings a way to do a calibration-free inference of distance. As a result, a calibration-free mapping of the expansion history of the universe. In third generation detectors with gravitational wave sources such as from Einstein telescope and Cosmic Explorer, this is my student Afroz, who has shown that how well we can measure the redshift evolution of dark energy equation of state as a function of redshift for a variety of model and different sources, which includes neutron star, black hole, and binary neutron stars. The main take home you have to remember is if there is a probe which I can go at different distance, measure its redshift and make an inference of the h of z, it's a direct trace of the expansion history. As a result, the dark energy equation of state reconstruction becomes a part of the story, but I can do a full reconstruction of h of z. And when you compare such results with other upcoming surveys, this is the error bars feasible from DESI, Euclid pessimistic, optimistic, W first baseline and extended, in comparison with what gravitational wave can bring to us in the future. It tells us that even the best measurement of dark energy from W first will be not as competitive as what we will be expecting from Cosmic Explorer and Einstein telescope, such as from sources with binary neutron star and neutron star black hole. Binary black holes are not that great because they are ultimately going to be limited by the errors we have in the galaxy surveys as well. But the main take home that you should possibly remember from this slide, that if you would like to like a standard model of cosmology where you have measured precisely dark energy equation of state, you would like to use a probe which is most calibration free and least susceptible to systematics. A way to get that is using gravitational wave signal. Another important part is about gravitational lensing of gravitational waves. Dark matter is one of the most dominant contribution in the universe which gravitates. And one of the things which you absolutely didn't have any idea. There are several ways to measure dark matter, possibly by interaction with standard model, but it goes without saying it is an assumption. Without that assumption, I really do not know how dark is dark matter, but one thing I know, it gravitates. And a direct probe of gravitational effect of dark matter is through gravitational lensing. What really happens, thanks to the gravitational wave observations, is a very interesting thing. The largest wavelength of electromagnetic observation is in radio, which is about few meters, is smaller than the smallest wavelength of gravitational wave, which is of the few hundreds of kilometers, which is seen from LIGO. As a result, the structure of the universe that you can probe using gravitational waves is very different from than what you can probe from electromagnetic observation. We will probe what electromagnetic observations are probing, but we will probe even more by the effect of microlensing on top of the strong lensing effect. This particularly happens when the wavelength of the gravitational wave is comparable to the Schwarzschild radius of the lens. And as a result, I start getting interference pattern in the gravitational wave, which is never happens for most of the EM observations. This brings a direct window to the substructures in the universe. It is Ayuba who has shown it for the first time on what we have from the LIGO data. It is the first model independent chromatic or achromatic test. This is now published on GWTC3. These are all the events we have so far. He has found that one of the events shows a mild 2.9 sigma, discovers the eye of the borderline. We found something like 2.9 sigma, we don't find very interesting. We went and did a parameter estimation of the lensing properties, and it shows that it's not very interesting right now. But possibly in the future, these avenues will tell us about the substructure and the population of micro-lensed or chromatic lensing signal from LIGO, and of course from CET. I have little only time left, maybe 2 more minutes. I will talk about one of the very important unknowns in the universe. At least when I always say this, that much bigger problem in cosmology is not only about Hubble tension or sigma 8, possibly the high redshift universe. I mean, we have seen black holes at high redshift universe using quasars, but we do not know how it is evolved and formed. So one of the really important aspects to understand is if I now put black hole masses as a function of cosmic time, I will observe by all these different windows from LIGO to PTA how the things evolve in this particular plane, how things have grown in the universe. We should not forget that that's an important piece of information which should agree with our standard model of cosmology. Along these lines, there are some recent exciting results showing first inference of redshift dependent black hole mass spectrum. This is a work by Christos Karanthesis. This was PhD work a couple of years back, where he shown that as a function of cosmological redshift from LIGO Virgo Cagra, is there any signature of redshift evolution of the mass spectrum? It is not yet strong, because we have only 90 sources, and out of that about 43 of them are above SNR of 12. But we are getting to a scenario where soon we have few hundreds of sources. So the question about is the black hole's mass spectrum evolving in the stellar mass end, we have a answer to that. More interestingly, not only about posterior distributions, now we can start talking about formation channels. This again, of course, is a work which is first time showing the black hole phase space. See, don't think about just probability distribution of masses. Think about how mass spin evolves as a function of redshift. When you think about stars, stellar physics, we do not talk about just probability distribution. We talk about HR diagram, an observable window of two quantities that gives in the trajectories of different formations. This is a scenario where you have, in terms of different direct observable quantities, we have constructed the phase space of binary black holes to show how different formation channels will show up, and if they form up to an extent very distinct region, and as a result this maps to a probability distribution of black holes in the universe for both astrophysical and primordial black hole. This table tells us for different color how can I assign probability of possible formation channel, and there is always a degeneracy. We cannot break that at this stage. Moving on to the supermassive black holes, so we have an open question in the area to understand how these black holes are forming, how heavy they form and how early they form. We have seen quasar observation from very high redshift, which tells us that okay, there is a bare black hole, and how they have really evolved we do not know. But long story short, the competition is between accretion or merger. How these things two are happening. If it is accreting, gravitational wave is not a very huge signal respect, rather no signal, almost no signal. But for merging, yes. So if black holes are merging from small structure to large structures, how many of them form how early in the universe? The work done by Mohit, so we'll not talk about the details, it has gone through a lot of hydro simulations connected with large scale structure distribution, showing you that in future with square kilometer array, these lines, and these are with the current pulsar turning array, we can make an inference of the genealogy of supermassive binary black holes, how fast they are growing and how massive they are. This tells me that these are the redshift evolution of the masses and its connection with the stellar mass. We will be able to make for the first time measurements as a function of redshift of black holes growth using a square kilometer array in the coming years. So interestingly, a completely unknown area where now we have almost 100% error bar, we start getting measurement by basically asking, for in the nanohertz data, are we seeing more signal coming from high redshift or low redshift by seeing a synergy with LSST and SQA galaxy service. And by cross of these two quantities, we can get a measurement of its redshift evolution. I think I rushed about this part a bit more because I don't have much time. What I would like to tell you is that probing the cosmos with stellar graviers is just a new area now. In low redshift with individual objects, at high redshift with stochastic background, and this is just going to grow excellent with the upcoming already unknown detectors and in future with LIGO India. And we should not forget about the synergy with several of electromagnetic probes where they play an excellent role in what I call as the area of multi-messenger cosmology. With this, I will end my talk. Thank you so much.